Hello everyone, welcome to this session. I am Aarti Swamy, Assistant Professor from Department of Electronics and Telecommunication Engineering from Walchand Institute of Technology, Solapur. So, in this session, you will be understanding the working principles, state sequence of digital counters and Johnson counters, and also you will be able to understand the ring counter and Johnson's counter state diagram and compare them in a practical way, how you can use it efficiently in a specific applications. So, this will be the learning outcome of this session. Next, contents. So, I will make you go through a roadmap or a session map where we will be going through introduction to counters, which is a basic. Next, ring counters, what is the block diagram of ring counters, what is the state diagram of ring counters, truth table of ring counters, timing diagram and their advantages, disadvantages, and finally application. So, this will give you a overall flow how a ring counter exactly works. Next, same thing we are going to do with Johnson counter. We are going through block diagram, truth table, timing diagram, their advantages, what are their disadvantages, and finally what will be the application of Johnson counter. Okay, to begin with basics, counters. So, in everyday life we go through many examples of counters, but we exactly don't know that it's working with counters. Like for example, the digital clocks we are using, or the light signals, traffic signals which we see on the roads, or even the LED lights which we use for decorations. All of these works with the help of counters. So, basically the counter is a backbone of all this. So, what exactly is this counter? Counter is nothing but a sequential digital circuit that counts clock pulses. So, what exactly this means? This means that, for example, say you are sitting with your friends and you are clapping your hands, and one of your friend is counting how many times you clap. So, clapping your hand is nothing but it's working like your clock pulse, and the counting which your friend is doing with the help of fingers is nothing but the flip flops. So, you're counting like 0, 1, 2, 3, etc. So, this is how a counter works. So, it basically counts. So, it's how is it constructed? So, counters are constructed with series of flip flops, like one flip flop connected to the next one and the other one. So, these flip flops are usually D flip flop or else JK flip flop. So, this is how basically a counter is constructed. Next, how this counter changes. So, like from 0 to 1, like for example, you clapped, you stopped, next once again you clapped. So, that is like you are changing the states from one state to another state. So, that clapping was nothing but your clock pulse. So, same way in the counters, the clock pulse changes the state from one state to another state. So, we see counters count 0, 1, 2, 3, 4, 5, 6 and 7. But what if we don't want this sequential countings, we want something like one hot count or double sequence learning. So, during that time, when we want like specific or a different type of countings, we go with special counters. So, special counters are nothing but ring counter and Johnson counter. So, this ring counter and Johnson counters are something called as a special counters which come in counting than our usual binary counters. So, our usual binary counters were 0, 1, 2, 3, but these special counters are something different when we compare to our binary counters. So, first when we come to ring counters, so it is nothing but one hot counter. So, what is this one hot counter? One hot counter is nothing but like one of the input is high at one time. So, for example, say you are sitting in a circle playing passing the ball. So, during passing the ball, what happens? One of them is whistling, right? So, whenever the whistle starts, you pass, and whenever the whistle stop, you stop. So, only one person is having a ball at a time, right? So, all the like if you 6 people are sitting in a round, all the 6 people are not having the ball in their hands. Only one people is having one person is having a ball in their hand. So that is nothing but your one hot counter. So it means only one is active or hot at a time. So that's why it is named as one hot counter. So now when you come to ring counter, it's nothing but a type of shift counter or a shift register counter. So now if it is similar to your shift register counter, then what will be the difference between a ring counter and a shift register counter? So what happens in your shift register counter, I think you guys will be knowing that in shift register you give a one input, it is also a combination of flip flops. So if you give one input, it will shift to the next one, then next one, then next one, and finally the output, right? So but in ring counter what happens, you shift, and in the end, instead of giving the output, that output is connected back to the input of your first flip flop. So that is nothing but is acting like a ring. So that's why it is named as ring counter. So that's what the output of the last flip flop is connected back to the input of the first flip flop. So this is the construction of a ring counter. So in this what happens, only one, either 0 or 1 is rotated. So from one to next state, from next state to the other next state. So like that. So in this, in counters what we had, basically the number of states were defined with the help of 2 power n, that is n is nothing but number of flip flops. So if you have 4 flip flops, 2 power n, so 16 states. But in ring counters that will not be the case. So for example, in ring counters you have 4 flip flops, okay. So 4 flip flops will give you 4 unique states, okay. So it is not going to double or anything. So if you have 4 flip flops, 4 state, if you have 8 flip flops, 8 state. So if you, the n bit or the n flip flop is going to represent the n number of states. So that's how a ring counter. So next, so this is basically the block diagram of a ring counter. So we are taking 4-bit ring counter. So we have 4 flip flops, flip flop 1, 2, 3 and 4. So here we are doing with D flip flop. So we have designed our ring counter using D flip flop. So we know that the D flip flop is a simple storaging. So whatever we give in the input, so that's going to act as our as output. So we say now this is our clock. So it's a negative edged flip flop, and this is ORI. So here in ORI we have connected our clear and preset. So whenever we have this, we want our ORI should always be low so that we get a high input. So that's why we are making our ORI as low for the first state, so that we get 1 in the QN state. So when we get 1 in the QN state, all the remaining states, that will be 0, 0, 0. So that will be our first state. So here you can see in the state diagram that our first state is what? 1, 0, 0, 0. Now after getting the first state, so this one is going to move to the next flip flop. So then this flip flop will be 0. So next flip flop we have 0, 1, 0, 0. So next again this one will move here, then this one will move here. So in the finally we will have 0, 0, 0, 1. Then this again, if it move to the first flip flop, again we will get 1, 0, 0, 0. So this is how basically a ring counter works. That is nothing but it's in the circular shape. So that's why it is called as ring. So it's in the form of a ring. So this is the state diagram and this is the block diagram of ring counter. So next let's move and see what is the truth table and the timing diagram of a ring counter. So as we said, whenever our ORI is low, irrespective of clock or the inputs, whatever you have, you will get your first flip flop output as high, that is 1. So all the remaining clock pulse, all the remaining output of the flip flops will be 0, 0, 0 in the first state. Next, in the second state, you will get this one will move here and this Q4's out 0 will come to the Q1's place. So you will get 0, 1, 0, 0. Then this 0 will come here and this 0 moves forwards. So that's why you will get 0, 0, 1, 0. Next, this 0 of Q4 will be moving to Q1's first place, that is 0. So then this 0 will come here, this 0 will come here and this one will come here. So we have that as 0, 0, 1. So this will be a third state. So now this is end. So again in the next clock, again you are going to start from beginning. So that is 1 0 0, 0 1 0 0, 0 0 1 0 and 0 0 0 1. So this is how your ring counter works. So it is just moving from one place to next state, from this state to this state. So you can see that it is proving our one hot counter. So you can see in the first state only 1 is high. In second state only Q2 is high, in third state only Q3 is high, and in next state you have only Q4 as high. So at one time only one of the state is high, that is one of the flip flop is high. So that's why it is called as one hot counter. So when you see the timing diagram with respect to the truth table, so we have first one as clock, next we have taken Q1, Q2, Q3 and Q4. So that are the 4 outputs of our 4 flip flops. So when you come to Q1, what is the value of Q1? So first the Q1 is high. So that's why we have given high here, and 0 0 1 0 0. So that's how your ring counter works. Now advantages. It's a simple design. Only one flip flop is active, so it is very easy to decode. And what will be the disadvantage? The disadvantage is flip flops are very like few states, right? So you can't, so there is a wastage of states also. And application is traffic light control. In traffic light you can see only one LED is on at a time. So and LED chaser. LED chaser is nothing but the LED lights when used for decoration. Next, this is the example of your simple ring counter. So you can see one of the thing is high at a time. So next, twisted ring counter, that is nothing but Johnson counter. It is similar to your ring counter, but only thing is it's a twisted form. So a simple twist is there. What is the twist is that in ring counter you are connecting your output of the last flip flop to the input of your first flip flop, but in twisted ring counter you will connect to the inverted output of your last flip flop to the input of your first flip flop. That is what going to make it a unique thing than compared to ring counter. So that's going to give you a unique sequence of states. So in this 2 power n states are produced. So example, if you have 4 flip flops, you will get 8 states. So here you can see this is the block diagram of your Johnson counter. So here you can see 0 0 0 1. So 0 0 0 0 is the first state. From first state you will give 1, so it will be 1 0 0 0, then 1 1 0 0, so 1 1 1 0, 1 1 1, and then again you will start emptying. So it's like basically you have 4 glasses, so you start filling with first glass, then second glass, then third glass, then fourth glass, then you will start emptying. So you will empty the first glass, you will empty the second glass, you will empty the third glass, and you will empty the fourth glass. So it's basically the same thing, how the Johnson counter works. So this is your truth table and the timing diagram of your Johnson counter. So you can see first state is always 0, then 1 is high, then 0 0, then 1 1 0 0, then 1 1 1 0, then triple 1. So you will start emptying now. You will empty the first state and all the remaining are high, then you will empty 2 states, then high, 3 states, then high, then all 0 0. So this is how your Johnson counter basically works. Now when you come to advantages and disadvantages of Johnson counter, so in ring counter we saw that n flip flops will give you n states, so it is not that effective or efficient. So in that, to overcome that, Johnson counter has 2 power n states, so that is more efficient use of hardware. So that will be advantages of Johnson counter. So it has built-in error detection, like whenever you have an error in any state, so it is very easy to detect in Johnson counter. But when you come to disadvantages, the complexity is very much in Johnson counter, like for decoding the logic, and even it's slightly hard to design or test, like which one is working or which one is not working. So when for applications you have digital clock, like when or pattern generator, like in countdowns, digital countdowns, you can see that there is a pattern followed, or during a match you can see the display of scoreboards. That is all the example of your Johnson counter. So this is simple working of Johnson counter. So you can see your first one LED is on, next when your second LED will be on, next your third LED will be on, so next your fourth LED will be on. So this is how your Johnson counter works. So you can see here, so the first LED will be off, second will be off, third will be off, and then finally the fourth will be off. So this is how your Johnson counter works. So these are the references. Thank you so much.